Hi, I'm Hassan, the lecturer here at the Institute of Medical Education, and today we're going to take a look at solutions to Section 3 of ACER's GAMSAT Green Booklet, Practice Test 1, specifically Unit 35, questions 106 to 108. And in this unit, we're going to take a look at Graham's law of diffusion and effusion, and we've been told that the relationship between diffusion and effusion is that they're inversely proportional to the square root of the gas's density or their mass. So if we can write it here as E, or let's say D, is inversely proportional to 1 over the square root of the density or the mass of the gas. So just before we dive into question 106, I think it's important we make note of the stimulus in 107, the stimulus required to answer 107 and 108. Please note that we're told in passing that the time required for effusion to occur is inversely proportional to the rate of effusion. I mean, we can write it like this, but we'll go through it in question 107. But just before we dive into 107, I think it's important to note this rule. So for 106, we're just told to simply find out what the relationship or the difference is between the rates of neon and krypton. So we're told that the densities of neon and krypton are 0.9 and 3.74 kilogram per meter cubed. We don't have to write the units for this question. I know I do harp on about it for every other question, but here we don't need it to answer the question. So I think the most important thing is here we just need to find a number that's easily square rooted over here so we can calculate the rate of diffusion. So the easiest way is to get whole numbers. So we've got 0.9, let's make it 1. We've got 3.74, let's just make it 4. So if we want to calculate now the rate of diffusion for neon, it's going to equal 1 over square root 1, which equals 1. And the rate of diffusion for krypton is going to be 1 over square root 4, which equals 1.5. Therefore, the answer for 106, neon is going to have a rate of diffusion that's twice that of krypton. So the answer has to be C. So now if we move on to question 107, which I alluded to earlier in the intro, this question is a bit of a mind trick. It's a brain teaser. But if you work through it systematically, we can get the answer. So it's telling us we've got gases X and Y, densities dx and dy, and they're both measured at the same temperature and pressure, which means we can use Graham's law of effusion here. The gas is placed into a apparatus and the time taken for a certain volume to be released is measured. We've already been given now that the time taken to release a certain volume of gas X is Tx, and we've got for gas Y is Ty. We've been given the ratio of the time. So they're telling us the ratio is Tx over Ty. So recall in the stimulus it tells us that the rate the time required for effusion to occur is inversely proportional to the rate of effusion. So let's just take a step back and let's just write down these equations here. So if the rate of effusion is going to be inversely proportional to the time, we already know that the rate of effusion is also inversely proportional to the density or to the mass of our gas. So we can write this as, let's say our rate of effusion for X is equal to 1 over square root its density, which also equals, remember, it's going to be inversely proportional, so 1 over time for X. The same could be written for Y. So it's the rate of effusion for Y is inversely proportional to the density of the gas Y, which is also equal to the inversely proportional to the 1 over the time, so Y. So we have these two equations now. So we've been given this ratio. So how do we achieve this ratio? So the easiest way to look at it is that because it's Tx over Ty, and we know that the rate of effusion is reciprocal, it's going to be flipped over, we know therefore that the equation is going to look something like this. Therefore, you'd have to do EY over EX equals, now if we're going to divide EY over EX, what we're going to do, remember, is that we're going to divide this. So let's try it for time. So it's going to be EY over EX. So it's going to be 1 over time Y divided by 1 over time X. And we know reciprocals, we can rewrite this as 1 over time Y times, so flip this over. So it's going to be times, or Tx over 1, or just Tx. So we know, therefore, that's going to equal Tx on Ty. So we know straight away that the rate is, if you do Ey over Ex, it's going to equal Tx over Ty, which is what we have here. But the question, what we're looking for is for the densities. So what's it going to be in terms of the densities of the gases? So it's the same principle here. So if we do Ey over Ex equals, again, we've got 1 over square root d, so the density of y, divided by, so Ey divided by Ex. So Ex is 1 over the square root of dx. And again, the reciprocal, so it's the same as the reciprocal, which is 1 over square root dy times 1 over square root dx. And therefore, 1 over dx. Sorry, let me just fix that up. Where's our tool here? Sorry about that. So what we're going to have here is 1 over dy, the reciprocal of 1 over square root dx is going to be times square root dx. So therefore it's going to equal square root dx over square root dy. So you can see, therefore, our final equation, what it's going to look like is, if I write a big box here, our final equation is going to be Ey over Ex equals, so the effusion rate of y over the effusion rate of x is going to equal the time, which we calculated here, x over time y, which is going to equal, this is the same as saying square root dx over dy. So, there are other ways you can conceptualize this. The easiest way in the GAMSAT, just to save you time, would just be like, look, if it's inverse the effusion, we know that the effusion is also inverse of the mass. So you know it's going to be the same thing. But the trick is, because you're dividing by each other, you've got to flip them over. So that's where, that's, I guess, how you can answer this question the long way. In the GAMSAT, you can just, again, conceptualize it. But if you wanted the long way to calculate, this is the way to go. And therefore, the answer for 107 is going to be A. So now we can move on to question 108. And the good thing about question 108 is we're going to use the same equation here. So we're going to use the same derived equation. So the density, or in this case, they've given us the mass of our atomic mass of our gas. So we can use this equation to solve. So we can use the equation, obviously, of time x over time y equals square root the mass of x over the mass of y. So we're going to use this equation for 108. So let's just clear the screen here. I might get the whiteboard out, actually. Actually, no, we can do it here. So remember, Tx over Ty equals square root, or the density, or the mass x over mass y. So that's the equation we're going to use for question 108. So it's telling us at a certain temperature, so 50 moles of a gas, so this is the unknown gas. It has an unknown, it takes 250 seconds to pass through a small hole. So we know that it's going to take 250 seconds. We know that under the same conditions, argon's going to take 100 seconds to pass through this hole. So let's just say argon's going to be x, because it's our known, and our y is going to be our unknown. So let's just say x is our argon and y is going to be our unknown. So if we're going to do Tx over Ty over Mx over My, we know Tx for our argon is 100 seconds, which it tells us there. So 100 I mean, you can write the units, but again, you don't have to here because it's not expressed in units. But if you do want to practice, you can write the units here. It's going to be 100 seconds over 250 seconds of our unknown. I mean, they do cancel out regardless anyway. Equals square root our mass of our argon, which we know is going to be 40. So that's the molar mass or atomic mass over. I mean, they don't give us the units for our atomic mass, but if they did give the units, you can include it in here, but they will cross off anyway. So 40 over x, so that's our unknown or our mass y. So all we got to do then is, I guess, if you want to remove the squared here, I'd probably write it as, it's easy to write this as 100 goes into 25. So it's going to be, so 50, so 50 is 2. So 2 over 5, and then we can square it. So get rid of that, equals 40 over my. So then what we can do is just cross multiply. So 4 over 25 equals 40 over my. So therefore cross multiply, it's going to be 4my equals, so therefore 4my is going to equal, so 40 times 25, it's going to be 400, 800, plus 4, 8, 12, 16, 20, 1,000. So it's going to equal 1,000. So therefore it's just going to be my divided by 4 equals 250. So our answer is going to equal 250. Well, the molar mass, well, it's supposed to be in grams per mole. I'm assuming this is going to be grams per mole. They didn't say so in the unit, but it would be grams per mole. So we'll just make the assumption it's going to be 250 grams per mole. So therefore, our answer for 108 is going to be D. So this unit was very mathematics intense. But again, if you just take a systematic approach, read the question properly, and go back to first principles, you'll be fine in answering these questions. So if you do have any more comments about, I guess, Graham's law of diffusion or effusion, or any other comments about the unit, you can post them in the comment section below, or you can contact us directly. We'd love to help. Thanks for your time. Bye now.